should be going up to up there. 4 of that. Okay. All right, everybody, welcome. Hey, and Lisa's here. Nice to see you, NB. Got people here already. Excellent. It is, 8:30 out here in Washington, D.C., just outside the nation's capital here. And we're going to do some chemistry tonight. One of the members to my channel asked me about gas laws on Tuesday, and I thought, I haven't really done anything on the gas laws, so that might be a good place for us to spend some time tonight, because they do come up on the exams quite frequently. So we're going to look at the gas laws this evening. At the end of the stream, I'll also try to jump over to the Discord server. I have a link that should be, you click it and you're right in the server. We'll see how that goes. Always testing new things, so we'll see if that works out. All right, so let's do some gas laws here. And check in the chat, say hello so I know who's here. If Jason or Loretta, Ioro, or Wesley, any of y'all are here, please say hi. And we'll go over to the gas laws. All right. So for the gas laws, we're going to look at 6 or 7 problems over 20, 25 minutes, not spend a really, really long time on it. And what we want to do is both conceptually kind of understand what's happening with some animations, but then also be able to do these equations. So the first thing that you want to think about is, how do you know air actually exists? It's kind of a weird thing, right? You can feel it in front of you, you can move your hand and feel it, but how do you know there's actually air molecules? Hey, Shamina, welcome to you, and John Ray, and some letters I can't quite read, but welcome. Here we go. So take a look. If you have a 1 liter bottle here, it's full of air, and I know it's full of air because when I try to squeeze it, it's got a cap on it. I can only compress it a little bit. Something is stopping me from pushing it down the whole way, and that's the air. So we know that the air is in there because it's preventing us from crushing the bottle. Bang. So that is how you know that there is air. That's one way that you know there's air. And if you kind of think about it, here, let's pull up the screen here. We can go to this animation, and I'll drop this animation in the chat. Here's our container. This is like our bottle here, and we can make it bigger or smaller. There's nothing in it right now. It's a vacuum. Hey, Jason and Loretta, good to see you. Let's put some molecules in there with our bike pump. So there's some molecules, or this maybe atoms. And we'll put a few of these other smaller, lighter ones in. And you see how they spread out. When they hit the sides of this container here, that's pressure. That's what pressure really is. As a chemist, I think about pressure as molecules colliding with the side of the container. And if we make this smaller, like when I squeeze the bottle, watch over here what happens to the pressure. So I'm going to decrease the volume. See how the pressure is going up? It's at 42. Let's decrease it some more, up to 53. And you see that there are more collisions with the side. The more collisions, the greater the pressure. And Jason, you're right. Nitrogen is the most abundant element in air. It's N2, though. It's diatomic nitrogen. Uh, hey, someone from Kurdistan. Excellent. Perfect. So as we decrease the volume, the pressure goes way down. So as you think about it, as you're thinking about pressure and volume, when we squeeze this, the pressure, that's the air molecules, the nitrogen and the oxygen molecules hitting the side. That's what creates pressure. And if you can remember that, a lot of the equations, they make a lot more sense. So let's do a problem here. I'm going to turn this off because it just kills my processor. There we go. All right, so first one, Boyle's law. Actually, we just did that one. So give this a try. See if you can work this out. Oh, I should write what Boyle's law is for you, though. P1, there's our pressure. V1 equals P2 V2, initial and final. So see if you can set this up. You don't have to work the math out, but see if you can set it up. Oh, there I am. All right, so when we're looking at this, they're saying that there's a fixed amount of gas and temperature. That means they don't change. So our pressure 1, let me move this down here. Pressure 1 would be 4.500 atmospheres times the volume, which is 17.50 milliliters. Let me move this over so we have a little room here. And that ends up equaling, what do we got? What's our pressure 2? We don't know. So we don't know pressure 2. And then volume 2 is 10.20 milliliters. And so since we have milliliters on both sides, we don't need to convert that to liters or anything. So we're going to go with dividing both sides by 10.20 milliliters. So that cancels out. That's gone, milliliters gone. So you'll be left with ATM. You know you did it right. So if you get the right unit, you know everything canceled out. And I end up with, did anyone get an answer for that? I end up with P2 equals 7.720 atmospheres. That's the answer I get. So this first P1, V1, that's kind of you always see a Boyle's law question on tests. Teachers just like it. And here's the curve, which you can see too. As the volume gets smaller, the pressure goes down. If the pressure gets bigger here, then the volume gets smaller, just like we saw there. Jason, you got 7.72. I think you need one more significant digit and you're there. So excellent. All right. So that's Boyle's law. The next law is Charles' law. And Charles' law says that volume and temperature are inversely proportionate. Hey, Huang is here. Excellent. And Vincent, glad that you did well on your exams and my videos helped you. That always makes me happy. So give this one a try here. This is Charles' law. And if you can set this one up, and then maybe I can show you this here, this demonstration in a second. So give it a try. Yep, I'm right, you're wrong. You got it, but you need one more significant digit, I think, on that. Hope you already have it. I see it there. Excellent. Hey, Mohit, welcome. I do not have the playlist for that, unfortunately. Yeah, I haven't done a lot of playlists. I should do more of them. All right, let's see if we can solve this one. So in this one, you would have to say that your pressure is constant and your amount of substance is constant as well. So we're just going to assume that. Yeah, they say the amount of gas and pressure is constant. So you don't need to worry about those. Hey, Vicky, congratulations on the exam. All right. Let's set this up. V1, so has this, and we want to know what happens if we get our new volume here. All right. So 20.5 milliliters is the volume, and the temperature is 40.0 degrees Celsius. V2, we don't know. We're finding the new volume. And the temperature is 65 degrees, 65.0 Celsius. And Ryan, you ask you make a very good point, and I was just getting to be there. It should be in Kelvin. In this case, because these degrees are going to cancel out, we probably would be okay, but I would recommend always changing stuff to Kelvin. So we could say 273.15 plus this number here. That would end up with having Kelvin in the bottom. We'll talk about Kelvin more later. When I did this without Kelvin, I did it, I think, in Celsius. I ended up with 21.8 milliliters. So if someone wants to try to do that in Kelvin and see if you get the same answer, that would be interesting. So that's the answer I got in milliliters here, and that's because we started in milliliters, and the units should work out there for you. All right. So let's look at this. Let's see if we can visualize this here with our app. So what we're trying to do is we're going to put some stuff in here. Let's put some of these in here. Let them kind of get equilibrated. And so what's going to happen, we're going to hold, I think we can just hold pressure constant. Hold one thing. We want temperature and volume. So if I take the volume and move it, the pressure changes. We know that from Boyle's law. But what if I heat it up? Oh, that's changing the volume, right. So if I heat it up, the molecules, they'll move faster and they'll push on the sides more. Oops, doesn't like that. So as you heat it up, the volume expands. So as we cool it down, I think we broke it. As we cool it down, the volume would contract for us. So let me put this in the chat so you guys have access to it. Because if you're studying and you look at this, everything gets locked into your brain real well. All right, so I'm going to shut this off here because it makes my processor sad. All right, so in this case, I think you're okay with Celsius because they cancel out. But the problem with Celsius is if you get 0 Celsius, everything blows out. Yeah, and if you heat things up, you can make them pop. It's pretty cool. All right, so here's where we're really going. This is the one that you need. If you have the combined gas law, it has everything in it. So if you memorize the combined gas law and they don't give you temperature, you could just ignore temperature and use Boyle's law. Or they don't give you pressure, you could forget that, and now you have Charles' law. So in this case, this is kind of the one that helps you. If you memorize this, you've memorized all of them, I guess is what I would say. And Vicky, you're right. It moves fast. It has a lot more energy from that heat there. So give this one a try. See if you can set this up. Do note that the original volume was 300. That's the original. So those are your P1s. So give that a try. We'll go over that and see if you can get that. Sometimes when you're doing these problems, it's helpful just to label things up here. Oh, that's P2, T2, and then V2. Sometimes it helps you just to label them in the problem. That way you can kind of not get mixed up, because I tend to get mixed up with some of this stuff if I don't take my time and do it. And here they're nice enough to give you Kelvin. So we don't have to worry about it. I probably would on a test convert to Kelvin. So then on our final side, we don't know what V2 is, and let me put the bottom part down here, Huang, and we'll take a look. And that was 400K. If you do all the algebra, you divide, you cancel out, you should end up with liters as your answer. So you should end up with, let me move that over there, I got the right numbers. You should end up with liters as your answer. And for this one, I ended up with 18.8 liters. And I did that number because I had actually, I guess you would call this 3 significant figures here. So I wanted to have 3 numbers, Wang. So I would go 18.8 on that. That is our V2. So if I was advising a student to study this right here, I would memorize this one, because then you know Boyle's, Charles, Avogadro's, Gay-Lussac's, you know all the laws there. And T2, oh, thank you, Andy. I don't know what's going on with me tonight. So T2 we said is 200. I had 400. Sorry about that. You guys keep me honest. I appreciate it. There we go. All right. Okay. Thank you, Huang, and other folks for correcting me there. It shows you're paying attention. Teachers love that. All right, that's the combined gas law. I do want to show you this. This is, I don't know if you've seen this before. It looks oddly illegal. This is called a hand warmer. And what's kind of neat about this is that it's got, I think it's carbon tetrachloride solution in the bottom. And it's closed off here except this tube. So when I put my hand around it, it heats it up and the gas expands and it's going to push everything up the tube. So I'm not squeezing it. I'm just putting my hand around the base to let the warmth from my hand push it up there. And it pushes it all the way up, and then it even starts pushing the gas up too. It might even start bubbling. Yeah. So it's even actually pushing the gas up. So if I wanted to get it back down, what do you think I would do? So we'll see which hand is warmer. If I put my hand on the top, yeah, right, illegal. It's actually forcing it back down a little bit. No, it did. I think this hand is warmer. Maybe it's gravity. Anyways, it's called a hand boiler, and it really shows us that as the volume increases, as the temperature increases, the volume of the gas increases, and that's what's pushing this up. You can get these on, let me put it up and you'll see as it cools down a little bit. Eventually they'll equalize and it should run back down. You can buy these on Amazon.com for like $5, $3 or $4. They're easy to break. I've had students break these, 3 or 4 of them already. So anyway, yeah, see it's going back down as it's equalizing out. All right. Anyways, I like that. It's hand boiler. If you search on hand boiler, you can get yourself one and impress your teacher. Hold it vertical and hold both sides. So do you mean hold it horizontal, or like this would be horizontal? And I think what happens if you hold it like this, see this tube here on the end? That's where it has to push up. So if I'm holding it horizontal, it can't push it up there. And so if I hold it like this, and then I hold both sides, it's a battle of which is warmer, which seems to be my right hand. And so, yeah, so horizontal. Yeah, the horizontal just won't work because the liquid can't get up through the thing, and pressure will just push it down. It won't push it up the sides. Vicky, you ask what the use of this is. It has pretty much no use other than to look cool and maybe teach a little chemistry. So that's it. Yeah, vertical is the way you're supposed to hold it there. All right. I don't, yeah, in this case, it's not an isolated system in terms of external heat, Wang. You're right. So this would be, but the gases internally are closed. All right, so that's my hand boiler. Let's do a PIVNERT, PV equals nRT. My students always call this PIVNERT. And we're coming up on about 20 minutes, so this may be kind of where we wrap up tonight. All right. So the thing that messes with students with, I'm not even on my screen. Let's go to my screen. There we go. The thing that really causes students problems with PV equals nRT is that what happens is they get this R here. And R is a gas constant. It just makes the units work out real nice. So we need it to have all the units work out. If it says atmosphere here, you have to use the value of R that has atmospheres. So that's how you know which R to use. If it says atmospheres, use the R that has atmospheres in it. So N, you have to have moles. T has to be in Kelvin for this. If it's not in Kelvin, it's going to be incorrect. So see if you can set this up, and then we'll work it, and I'll share my answer with you, and you will have done a PIVNERT law. And this is related to the other laws as well, except now we have amount of substance in there. All right, give that a try. Hey, I'm right, you're wrong. Were you suggesting that I like turn it upside down? Let me try that. That's a good question. So if I put it like this, get all the stuff up there. And then what happens if I do this? It seems like it's trying. It seems like it's trying to get up there, but again, this thing isn't in the liquid. Somehow that's causing problems for it. Maybe there's more to this than meets the eye. Maybe there's some kind of scientific paper. Ah, I see. I got it. All right. So let's give this a try here. Pressure 0.8 atm. And the temperature, you can see to get Kelvin, I just add 273.15. But we're looking for the new volume, so we don't know what the volume is. Equals our moles. And I think we're going to need a lot more room for this, because here's R. And so you'll see R with this, right? You'll see R written as like over, this should be the -1. No, it's not. Sometimes you'll see it written out like this, a number of different ways, but it's liters atmospheres over Kelvin mole. And then what was the last thing? Temperature, which we said was 308.15 Kelvin. And so when you do this, you can see Kelvin is going to cancel out, moles is going to cancel out, and then when we get over on this side, we'll cancel out atmospheres as well, and we'll be left with liters. So that's why we need to have this R in here. Otherwise, our units just blow up. All right. So if you do all the math, I don't know if anybody got an answer for that. What is all the math? I end up with 0.537 liters for the volume. And you kind of, is that reasonable? Yeah, that kind of makes sense. I mean, it's not a big volume. 5 grams of neon isn't a whole bunch. Yeah, it's just a straw that goes to the bottom, exactly. And that's what confuses most students about this. All right, yeah, you got it. Okay, so I think at this point, we've been at it about 25 minutes. That's probably about the limit of your attention and my attention for the gas laws. Um, do take the time. Is it 0.0537? I might have this incorrect. I may have to redo my math. Someone else got a number for that. Please do let us know. So I'm going to jump over to the Discord server, and you're welcome to join me. Let's try that. It should be easier. I think you just watch for fun. Awesome. I think it should be better than last time, where I think the link I had wanted you to do log on or something. Hey, Akesh. So I'm going to jump over there in about 2 minutes. If you want to join me, last time we had some folks there. It was kind of fun. We chatted for a little bit. I'm just trying again, to just kind of learn how to use Discord. Maybe I might start doing some stuff on that later. All right, Cult of Saran, you're doing gas laws. Well, then this was fortuitous. Hey, Andy, good to see you here tonight. All right, so I'm jumping over to Discord. Thank you, everyone, for joining me. Next Tuesday, that'll be Halloween here in the United States. Who knows, maybe I'll dress up as Walter White or something. We'll stream again next Tuesday. And as always, this is Dr. B, and thanks for watching. I'm logging off. I'm going to jump over to Discord. Discord annoys you? I'm right, you're wrong. It annoys me right now, too, because I don't know how to use it very well. But maybe I'll learn. All right. Take care, folks.